this video we're going to look at a few more complex examples of how sine, cosine, and tangent are used to help us find missing values in a diagram. In this example we're given a rhombus has diagonals of 4 meters and 10 meters, and we're supposed to find the angle measurements of the rhombus. I put up here, recall, the diagonals of a rhombus are going to bisect the opposite angles, and the diagonals are going to bisect each other. What that means is that if this angle is x, then so is the one right next to it. Likewise, if this is angle y, then so is the one right next to it. And then my diagonals of 4 and 10 were cut into side lengths of 2 and 5. So what I'm going to look at is actually just one of these triangles. And remember, it's a right triangle because the diagonals are also perpendicular. And it's the right triangle that actually gives me something to work with. I have sides of 2 and 5. And I'm looking for the angle x and the angle y, and that means I can use my sine, cosine, or tangent. I have enough information here. Let's start with angle x. If I'm looking at angle x, the opposite side would be 5 and the adjacent side would be 2. Well, that means opposite and adjacent would be a tangent function, so I could say the tangent of that angle x is equal to the opposite side 5 over the adjacent side of 2. We learned in the last video that when I'm looking for an angle, I simply need to ask the calculator what is the tangent inverse of that ratio 5 over 2. And that's the same thing as asking what angle always has a tangent of 5 over 2. So I go to my calculator and I ask what is the arctangent or tangent inverse of 5 over 2. And I get that that's a 68.198 degree angle. For angles, we're typically just going to round that to a 68 degree angle. So I know that this angle in the corner is in fact 68 degrees. Going back to my rhombus, I then know that both of these angles in the corner are 68 degrees. I could do another sine, cosine, or tangent function, but I'm going to use the idea that if I'm looking at a right triangle and one of the acute angles is 68, 90 minus that 68 is going to give me the other acute angle, which in this case would be 22 degrees. So I can very quickly go back to angle y and say, well, that's 22 and 22. If my thinking is correct, let's just check this using a tangent function just to see if we get the same thing. If I'm looking at angle y, then 2 would be the opposite side and 5 would be the adjacent side. Remember, when you look at different angles, the opposite and the adjacent can switch places. So that's still a tangent though, because it's opposite and adjacent. So the tangent of that angle y would equal the opposite side of 2 over the adjacent side of 5. Here's another example where I need to ask the calculator, say, what is the tangent inverse of 2 over 5? And if my thinking is correct, it should be 22 degrees. So go to the calculator, and we're looking for the arctangent now of 2 over 5. Let me erase that. So 2 over 5, and look at that, it's 21.801. So we're rounding a little bit. That would round up to 22 degrees. So y is 22 degrees. A much quicker way would be what I did the first time when I said 90 minus 68 is that 22. Use those types of things to your advantage to be more efficient. Looking back at the rhombus, I now know what those angles are in the corner. Because remember, I was not just looking for the angles in the triangle, I was using the angles in the triangle to figure out the rhombus. I now know that this entire angle in the corner is 44 degrees, 22 plus 22, and I know that this entire angle over here is 68 plus 68, which would be 136. And that makes sense because the two angles that are next to each other in a rhombus should add up to 180, and 44 and 136 do. So the angles of this rhombus are 136 degrees, 136 degrees, 44 degrees, and 44 degrees. Remember, there are 4 angles, so I should list all of them.
but I know that this angle is going to be the same because it's opposite. I know this angle is going to be 44 because it's opposite. And in a rhombus, the opposite angles are the same. So there's an example that started out as a rhombus, but because of the right angles in that rhombus, I could get right triangles, which allowed me to use the tangent function to find my angles. In our next example, we're trying to find the base of an isosceles triangle that has legs of 12 and base angles of 65. The way that it's drawn, there's nothing that I can do, but remember, when you draw an altitude in that right triangle, it's going to cut that base in half. So this would be x over 2, and this would also be x over 2. Well, I'm going to draw just that right triangle on the side. So right triangle over here that has a hypotenuse of 12, and I'm essentially looking for this length. Then I can double it, and I'll be able to find x. This 65-degree angle is still intact. I have not cut it in any way. So what I'm looking at is a hypotenuse, and I called it A because that's the adjacent side to that 65. So the adjacent side and hypotenuse, that's a cosine relationship. So the cosine of that 65-degree angle should be equal to the adjacent side A that I'd like to know over the hypotenuse of 12. Again, I like to just treat cosine of 65 as the decimal that I'm going to get from my calculator and do the algebra first. I'd have to multiply both sides by 12 to get A by itself. So the cosine of 65 multiplied by 12 is going to equal my adjacent side A. So here's where I go to my calculator and I say, what is the cosine of 65? And that's 0.422. But I'm taking that 0.422, or the cosine of 65, and I'm multiplying it by 12, which is 5.071. So we're going to round that to approximately 5.1. Now I got to be careful. This is not the answer to my question. 5.1 is A, but A is equal to x divided by 2. That's where I have my relationship here. Those are the same length. So if A is 5.1, multiplied by 2 would equal x, that means that length of x is 10.2. So without sine, cosine, or tangent, there'd be no way to solve this, but since I do know that 65-degree angle, I can use my cosine relationship to figure out what that side is. Our last example is probably the most complex of all three of them. What I hope you notice here is that you have 3 different triangles to work with, and 2 of them are in fact right triangles. So I've got the right triangle there with the 35 degree, and I've got the big triangle that contains everything over here. So what I'm going to do is put that information in there and then give you my plan. This is 35 degrees with a base of 24. This is 24, and that's all I really have there. My goal is to find x, and x isn't even on a right triangle, so it seems like sine, cosine, and tangent won't help me. However, I'm thinking if I can find this side of y, and I can find the entire length of that big triangle, which I'm going to call z, and those 2 pieces are on right triangles, I'm going to use the relationship that x plus y is equal to z to figure out what x is. So let's look at our first right triangle here and see if we can find y. Y would be the opposite side of that 35-degree angle, and 24 would be the adjacent side of that 35-degree angle. Opposite compared to adjacent as a ratio is a tangent relationship, so that's going to be the tangent of that 35-degree angle is equal to the opposite side y over the adjacent side 24. Well, again, I'm going to solve this by multiplying both sides by 24. So when I do that, I get the tangent of 35 multiplied by 24 should equal that value of y. Here's where I go to my calculator and I say I want the tangent of 35, which is 0.700, multiplied by that 24, which is 16.804. I'm going to round that to simply 16.8 is equal to y. Now that's an important number, so I'm going to circle that and remember what that is. So y is equal to 16.8. I'm going to do the same thing to help me figure out z, but I have to be careful. This angle in the corner is not 35 and it's not 20. It's actually 35 and 20 combined, which would be a 55-degree angle. But I also have the same relationship here. Z would be the opposite side of 55, 24 would be the adjacent side of 55. So I'm looking at another tangent relationship. In this case, it's going to be the tangent of 55 is equal to that opposite side z over that adjacent side 24. So again, to solve this, I'm going to have to multiply both sides by 24. So I get the tangent of 55 times 24 is equal to z. Well, that's what I wanted. Now I can go to my calculator and simply say, what is the tangent of 55, which is 1.428, multiplied by that length of 24. And I get 34.275. I'm going to call that 34.3. And again, that's a very important number, so I'm going to circle that, because now I have the two numbers that I can use in my original plan saying that x plus y is equal to z. So let's fill in those numbers there. I still don't know x, but I figured out using tangent that y is 16.8. I figured out using tangent that z is 34.3. So all I really need to do is subtract that 16.8 from both sides. Make sure I get this right. So I'm taking 34.3 minus the 16.8, which is giving me 17.5 as the length of x. So using my tangent function twice, I can find that x is going to be equal to 17.5. So those are a little bit more complex problems. Do the practice problems in your workbook and see me if you have any questions, and I'm sure you will, because sometimes it just takes some playing with the picture to find what you need to do.